My name is Arnab Dhara, and my work seeks to understand how to efficiently combine deep neural networks with seismic inversion algorithms and exploit advantages of this hybrid approach.
Hello, my name is Andrew Gary, and welcome to Seismic Soundoff in-depth conversations in applied geophysics. In this episode, Arnab Dhara discusses his paper, Physics-Guided Deep Autoencoder to Overcome the Need for a Starting Model and Full-Waveform Inversion in the June issue of The Leading Edge. In this conversation, Arnab proposes employing deep learning as a regularization in full-waveform inversion. He explains why physics-based solutions with machine learning are challenging to develop, how he made it possible to train the network without known answers, and why he tested his approach with the Marmousi and SEAM models. Arnab also shares why this research took over 20 years to build on the initial idea and how he used full waveform inversion without a starting model. This is a cutting-edge conversation that may represent the future of FWI. So now, my conversation with Arnab Dhara. Well, that's a great lead-in to what we're going to be talking about today, which is an article that you published in June's The Leading Edge, where the special section focused on physics-driven machine learning. Why have physics-based solutions with machine learning been more challenging to develop?
Deep neural networks contain millions of parameters. They are algorithms that are designed to be trained with a lot of labeled data examples. Whereas physics-based deep learning often involves training these large neural networks with complicated loss functions, which generally consist of multiple terms and are thus highly non-convex optimization problem. Consequently, the training may not be robust and sufficiently stable, and thus convergence to global minima is not guaranteed. To resolve this issue, one needs to develop robust neural network architectures and training algorithms. Unlike classical machine learning problems like classification or regression, physics-based deep learning often involves sophisticated discretization techniques and derivative calculation. Although geoscientists have been developing such code for decades, they cannot be seamlessly integrated into modern deep learning frameworks like TensorFlow and PyTorch. A machine learning developer environment that can address the above issues could help more geoscientists to develop physics-informed deep learning algorithms.
It kind of makes sense why this paper is in the leading edge to help geophysicists. I'm curious, what did you want to learn when you started working on this paper?
Well, when I started this project, my goal was to combine physics-based geophysical inversion algorithms with data-driven machine learning algorithms and understand if either approach can add value to the other. Physics-based inversion algorithms are ill-posed problems and produce non-unique solution. The inverse problem becomes particularly challenging when you have noisy, incomplete, and band-limited data coverage, which is most of the case. Deep learning, particularly neural networks, produce robust results, but they need a lot of training data to make them work. I wanted to see if there is an efficient way to combine these approaches and understand if the building block of either of these approaches can help overcome the limitations of the other. And as demonstrated in my research, inversion algorithms can significantly benefit from neural networks.
Yeah, that's a great conclusion there that we'll get to shortly. Why did you choose full waveform inversion to work on this hybrid solution?
Full waveform inversion is the most powerful application of geophysical inverse theory. It seeks to utilize the full wave field to generate high-resolution models of subsurface parameters, such as compressional and shear wave velocities, anisotropy, and attenuation parameters. The application of FWI is widespread, ranging from exploration and earthquake seismology to areas even outside geophysics like medical imaging and non-destructive testing. In general, the inversion problem is computationally expensive and nonlinear, non-unique, and very ill-posed. We need a very good starting model, which is closer to the true model for FWI to work. Even though the theory of FWI was developed in 1980s, application to real and challenging datasets in a computationally feasible way is still an active area of research. Developments in areas like high performance computing and deep learning opens up new avenues to address some of these challenges. That is why I was interested in developing a physics-guided deep learning-based solution for full waveform inversion.
One thing that's pretty unique about what you were doing in this paper is you made it possible to train your network without known answers. How did you make that possible?
Conventional deep learning algorithms utilize large amount of paired seismic measurements and velocity maps to train the network. We do not require such labeled seismic measurement and velocity maps in our approach. We train our neural network using the misfit between the observed data and the synthetic data, as we do in physics-based inversion. The deep network learns the inverse operator. The synthetic data is generated by feeding the velocity model from the network into a partial differential equation solver that simulates the wave propagation.
What new input and output did you use for your model?
My network is an autoencoder architecture to which the seismic short gathers are given as input. The output from our network is a 2D matrix having the same dimension as the original velocity model. The output has values between 0 and 1. The output is finally scaled to the minimum and maximum bound of the velocity range. The velocity model is now given as input to the PD.
Could you share a little more about your encoder decoder architecture?
Yeah. So my encoder decoder architecture is designed using convolutional blocks. The seismic short gathers are given as input to the network in the form of channels. The encoder network then generates low dimensional feature maps through a sequence of convolutional blocks and max pooling layers. The decoder then transforms these feature maps into velocity models using a sequence of convolutional blocks and upsampling layers. Each convolutional block consists of two convolutional layers and two ReLU units. Each convolutional block outputs twice the input channels. The max pooling layer reduces the size of the feature maps by a factor of 2. Finally, the output of the encoder is connected to a linear layer that generates a 1D latent vector. The 1D latent vector is now given as input to the decoder. The convolutional blocks are interleaved with the upsampling layers. Each convolutional block outputs half the input channels. The upsampling layer increases the feature dimension by a factor of 2. The output of the decoder is fed into a convolutional layer that reduces the dimension to 1. This intermediate output is fed finally into a sigmoid layer that reduces the size of the output value to the range between 0 and 1. The output is finally scaled to an expected velocity range. The output of the network can be directly used in the partial differential equation solver without any post-processing.
What is the benefit of your approach over conventional full-waveform inversion?
Conventional full waveform inversion needs a good starting model and low frequency data for the method to work. Our method requires no starting model at all. Moreover, the performance of our method is robust even when we add noise to the data.
That's pretty impressive. Why did you test your approach with the Marmousi and SEAM models?
The Marmousi model represents a complex stratigraphy having lot of layers and different geological structures. Moreover, almost all publications on the topic of imaging and inversion in our community contains the result from the Marmousi model. We wanted to benchmark the performance of the proposed method on this standard model. We used a 2D portion of the SEAM model since it contains a complex salt body structure with rugose top, a root, and overhangs. The effect of cycle skipping and non-convergence in absence of a good starting model is all the more pronounced when you have large salt bodies. And the SEAM model provides a very good analog of such an environment in deepwater Gulf of Mexico.
Well, people are starting to hear the conclusion of this paper, but let's pull it all into one response here. So, what did you conclude from your research?
My biggest conclusion from this research was that we have not yet fully realized the potential of neural networks. Specifically to our study, where we combine neural networks with full waveform inversion, we showed the network can capture prior information from data, which acts as a regularization for our FWI. The regularization is strong enough to alleviate the need for any starting model for FWI, which has been the limitation of current FWI algorithms. We showed that our conclusion is true both for Marmousi model and the SEAM model, which contains complex salt structures.
You know, the idea for your paper had its roots in an article published 22 years ago in 2000, Why do you think it has taken so long to build on this initial idea?
Although the idea of using machine learning for inversion was introduced in 2000, the developments in the field of machine learning, particularly deep learning, has made it possible for us to apply it to complex problems like full waveform inversion. An important milestone within this journey was the development of convolutional neural networks and their application in computer vision. Also, availability of open source machine learning frameworks like PyTorch nowadays has helped me and other researchers. We can build and train a neural network within a minutes and use modern optimizers like Adam to train it. Finally, this development is also the result in the development of high performance computing architectures, especially graphical processing units, and their increased affordability means that research groups within universities can work with those.
How would you like, or how do you see other geophysicists and data scientists building upon this study?
In our study, we have used a simple convolutional layer based autoencoder architecture. So it will be interesting to see if other advanced machine learning models like transformers or invertible neural networks or generative adversarial networks can be used for this work and see if their performance is better than our model. Moreover, another area of research would be to see if we can include other kind of prior information, for example, facies distribution or migrated images to improve our result or significantly reduce the runtimes. The proposed approach can be extended for more complex full waveform inversion problems where we invert for multi-subsurface parameters like density and attenuation.
What new questions did you discover when using machine learning for FWI?
There are still several open questions. In our research, we showed that combining neural networks with FWI can alleviate the need of a starting model. But there is still a deeper need of understanding of the cause and the limits of this regularization ability and see if there is some limits of our research.
We speak to a wide ranging number of people on this podcast, and you're a PhD candidate right now, well on your way to an exciting career. As of now, what principal teaching or point of view has really helped set you on your path to be successful in this field?
The field of deep learning moves at a very fast pace with breakthroughs and new research emerging every other month. I try to keep myself updated about the latest research by going through machine learning conferences and journal publications at least twice a week. This has helped me with my research. I am reading geophysics publications regularly, and that has helped me understand the limitations of our processing and imaging algorithms and the different ways that researchers have taken to overcome the problems and how these approaches have evolved over time. That has helped me to develop hypotheses for my own research regarding the application of machine learning to inversion and develop an understanding of the benefits and challenges of the proposed approach. I try to keep my hypothesis broad and question all kinds of possibilities. This has helped me solve some of the problems which were previously deemed unsolvable and challenging.
Well, that sounds like that type of mentality is going to set you up for long success in this field. So, Arnab, I appreciate you talking about the paper that you worked on in June's The Leading Edge that we'll have linked in the show notes so people can read it. And excited to see what you start working on next.
Thank you, Andrew.
SEG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Gary at 51 Features. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.